in chapter 9, we are talking about something completely fresh, completely new, you have never seen before. So it takes a little time to um, learn this concept from the start. Okay, and we're going to use the tools from calculus, use both derivatives and integrals or integration in this chapter when we talk the infinite series. So let's just start from the very basic thing of sequence in the first section. Okay. So what is a sequence? A sequence is a set of infinite ordered numbers. A1, A2, A3, you know. You just get the uh, infinite set of numbers in order. Okay, those numbers, you got the infinite numbers and they are in order. You know, a sequence, I think it's easy to understand. All right. You know, you can simply just write a sub n, you know, sandwiched by a bracket or braces. Okay, so that also means a sequence. And a sub n are the nth term of the sequence. You know, that's the general term of the sequence. So let's just talk about some specific examples of sequence. In example A, we got the sequence at n equals 3 plus -1 to the n. Okay, so when n is not specified, it automatically starts from 1 and then go to 2, 3, 4, and so on. So in this sequence, an, the general term an is 3 plus -1 to the n. That's the formula for the general term or the nth term of the sequence. So the first term for this sequence will be a1 and starts from 1 as I said. What I do is plug in 1 for n in the expression or formula for an. So that's 3 plus negative to the 1 if you plug 1 for n. So you get the 3 minus 1, which is 2. And the second number in this sequence will be a2, which is 3 plus -1 squared if you plug 2 for n in the formula of the sequence. So you're going to get the positive 1 this time to add 3. So you get 4. And then the next number in the sequence, 3 will be 3 plus -1 to the 3 if you plug 3 for n. And -1 to 3 is just -1, so you get 3 minus 1, which is 2. And a 4, you know, you just plug in 4 for n in the formula for 3 plus -1 to the n. That's the next number in the sequence. So you get the -1 to the fourth, which is positive 1. So 3 plus 1 is 4. So the fourth number in the sequence is 4. So if you just list the terms or the numbers of the sequence, you get a 2 as a1 and the 4 as a2 and 2 again as a3 and the 4 as a4 and so on. So you got a 2 4 2 4 2 4 2 4. That's the pattern of the sequence. Okay, that's how you you know write down the terms of the sequence. In the next example, you got another sequence Bn, and the form or general term or formula or expression for this sequence is n over 1 minus 2n. So again, we didn't specify what n starts, so that automatically means n starts from 1. So for the first term of the sequence Bn, you just start n equal to 1. Plug in 1 for n in the expression, you get the 1 over 1 minus 2 times 1. If you plug in 1 for n in this expression. So 1 minus 2 in the denominator is -1. So you get a 1 over -1, which is -1. So the first in the sequence Bn is -1. And the second term, if you plug in 2 for n in this formula, you get a 2 over 1 minus 2 times 2. And you get the 1 minus 4 in the denominator, so that's -3. So 2 over -3, you get -2/3. I mean, yes, negative 2/3. So that's the second term in the sequence. And the third term, n over 1 minus 2, and if you plug in 3 for n, so you get 3 over 1 minus 2 times 3. So 2 times 3 is 6. You got 1 minus 6, that's negative 5. 3 over negative 5, so that's negative 3/5. So that's the third term in the sequence being. And the next number in the sequence will be 4 over 1 minus 2 times 4 if we plug in 4 for n in the formula. So 2 times 4 is 8. 1 minus 8 is negative 7. 4 over negative 7, that's negative 4 over 7. So you got the sequence, starts from negative 1, and then negative 2/3, 3/5, negative 4/7, and so on. So that's how you write down the terms of a sequence. Any questions in this example? Let's go to the next page. All right. The next example is n squared. That's the sequence Cn. It's defined as n squared over 2 to the n minus 1. That's the general term, the nth term. So again, n starts from 1. In this case, you plug in 1 in the formula, you get 1 squared over 2 to the 1 minus 1. So in the denominator, you get 2 minus 1, which is 1. And then the numerator is also 1. So 1 over 1 is 1. So that's the first term in the sequence. The second term will be 2 squared root 2 squared over 1 if you plug in 2 for n in this formula of n squared over 2 to n minus 1. 2 to the square is 4, so you get 4 on the top, and 4 minus 1, which is 3 at the bottom. So we got the 3 in the second term of the sequence. The next term will be 3 squared over 2 cubed minus 1 if you plug in 3 for n in the formula. So 3 squared is 9, and 2 cubed is 8. So you get 8 minus 1 in the denominator, which is 7. So the third term is 9 over 7. And the next term will be 4 squared over 2 to the 4th minus 1 if you plug in 4 for the n in the formula. 4 squared is 16, and 2 to the 4th is also 16. So you get the 16 minus 1 in the denominator, which is 15. So the first term will be 16 over 15. So that's the first term. So then you get the actual numbers in the sequence. Starts from 1 and followed by 4, 3, 9 over 7, 16 over 15, and so on. So that's sequence Cn. The next sequence is a little different. We have a sequence Dn. I don't know, I got some this equal sign here under the D. But this sequence is defined in a different way. It's defined, oh, I see, okay. It's defined recursively. The value for the first term D1 is given to be 25, but then the other terms are defined based on a formula between d of m plus 1 and dn. So d of m plus 1 equals d of m minus 1. So that means you just subtract 5 from the current term dn to get the next term d of m plus 1. So remember, n and m plus 1 are the indices. It indicates the which term we're talking about. So d1 is 25. So to find d2, you need to subtract 5 from d1 according to the formula. If you plug in 1 for n in this formula of dm plus 1 equals dm minus 5. So d2 equals d1 minus 5, which is 25 minus 5. d1 is 25, so you get 20. And then you plug in 2 for n to get d3. So 2 plus 1 is 3. So d3 equals d2 minus 5. d2 is 20. So 20 minus 5 is 15. And then you plug in 3 for 3 plus 1 is 4. So you get a d4 equals d3 minus 5. But the 3 is 15, so 15 minus 5, you get 10. So you get the numbers of 25, 20, 15, 10, and so on in this sequence. Any questions? So a sequence can be defined in different ways. Okay. So these are some simple examples of sequence. All right. When we talk about sequence, we want to know, what these numbers going. Is there a limit for those numbers? Do those numbers in the sequence approach a limit? For example, if we have a sequence an equals 1 over 2 to the n, so again, you can write down the terms of the sequence by starting from 1 for n. So a1 will be 1 over 2 to the 1, which is 1 over 2. A2 will be 1 over 2 squared. If you plug in 2 for n in the formula, you get 1 over 4. And a cube is 1 over 2, 2 cube. If you plug in 3 for n, you get 1/8. And a4 is 1 over 2 to the 4th. If you plug in 4 for n in the formula, you get 1 over 16. So you can see the numbers get smaller and smaller. And at the end, you can imagine that the limit actually is 0. So all these numbers in the sequence will approach 0 in this example. And you can see this tendency of the sequence in the graph I just plot. So the red spots denotes the term of the sequence. So A1 is 0.5, okay. A2 is 1/4, that's 0.25, and so on. You can see this, these numbers get smaller and smaller, and at the end, all the red dots will approach the 0, right? So the limit of an is 0 as n approaches infinity, or we say that an converges to 0. All these numbers converge to 0. So that's the limit of the sequence. All right? Okay. So how do we find the limit of sequence? We can use, the limit of function to find the limit of a sequence. Remember, these are two different things. Okay. So the theorem 9.1 says, let f be a function such that the function has the limit of L as x approaches infinity. So this is the limit of a function. Okay, a function is continuous. A sequence is discrete. Okay, remember in the previous graph, I plotted points, discrete points for the sequence. Okay, but a function is continuous, like the curve in the graph. It's continuous. All right. So they're not the same. So we have function f with the limit L as x approaches infinity. All right. And at the same time, we have a sequence of an, and an has a relation with this function such that f of n equals an. Okay, f of n equals an. That means when you plug it in n for x, you get an. So that means if you plug in the function, the curve, and the sequence, the points on the same graph, then all the points of the sequence will be on the curve f of n equals an. Okay, the value for x equal to n is an. Okay, so so that means y equal to n. Okay, so if you plot the n an for x, y, right? Okay, x equal to n, y equal to an. That'll be on the curve. Okay, so in other words, the sequence is just some spatial points on the curve, as you can see from the graph. And then obviously the limit of the sequence will be the same as the limit of the function, okay? Because the other points are on the curve. So whatever limit for the curve is, then it has to be the limit for the points on the curve. So the limit of the sequence can be found by evaluating the limit of the function, okay? So a typical example is the sequence of an equals 1 plus 1 over n to the nth power, okay? So how do we find the limit of this sequence? We can let x, f of x equals 1 plus 1 x to the x. Just change n to x to make it continuous. So that's the function we have. Then obviously f of n equal to an. Okay, if you just switch back x to n, then you get an in the function. And we know from Cat 1 that the limit of f of this function, f of as x approaches infinity, is e. Okay, the limit of 1 plus 1 over x to the x power is e when x approaches infinity. And the numeric value for the number e is 2.71828, and so on. It's an irrational number. So then the sequence must have the same limit as the function. So the limit of the sequence is also e. Okay, so you can see, this curve will approach a value of 2.78, 1828. That's how it goes on the right side, as well as the sequence, the discrete points on the curve, right? Okay, so that's the limit of the sequence. Just like the sequence, the limit of functions, we can always add two sequences. So there are two sequences, an and bn here, and the sequence an has a limit of l, and the sequence bn have whatever k. Then you can find the limit of the sum of these two sequences, and that they are just the sum of the two limits of those sequences. And similarly, you can also, have the sequence from the difference of those two sequences, an and bn, and that also has a limit of L minus K, the difference of the limits of an and the limit of Bn. Or you can multiply any constant C to any sequence an and find the limit. And that's just the C times the limit in itself. Or you can multiply two sequences term by term, okay? So an times b1, and that gives another sequence, and the limit of this new sequence will be the limit of an l, which is l, times the limit of bn, which is k. Or you can divide the two sequences an and bn term by term and try to find the limit of this new sequence, and the limit of this new sequence, just the limit of an over limit of bn, which is l over k, and of course you want to you want the limit, you want the denominator bn and k both not equal to 0. All right, you cannot divide any 0. Okay, so this is very similar to the rules we had in Cat 1 for functions. Okay, when you have two functions, fx and gx, you try to find the limit of the sum, difference, or product or quotient of two functions. You do the same thing. Okay, let's talk about more examples of a limit of sequence. This time, we just go back to the previous examples we did when we started. The first example is the limit of an which is 3 plus -1 to the n, as we already did before. We know this sequence goes like 2, 4, 2, 4, right? If you just plug in numbers for n from 1 to 2, 3, 4, and so on, you get the sequence of 2, 4, 2, 4. Okay, so I'm not going to repeat that. We already did it. So you see, there's no limit for this sequence. It just jump between 2 and 4 forever. It doesn't. Those numbers do not converge or approach a limit. So with sequence diverges, and it does not have a limit. Okay, and the second example we did in previously, bn equals n over 1 minus 2n, and we try to find the limit of this sequence, and the way to do it is to divide n both on the top and at the bottom. Okay, I think you learned how to evaluate the limit of function before. This is similar. You try to divide the some big number both on the top and at the bottom of a fraction. So you get n over n, which is 1 on the top, and 1 minus 2n over n at the bottom. And that can be split into 2 terms, which is 1 over n minus 2n over n in the denominator. And obviously 1 over n is 2 if you cancel the n. So we got the 1 over n minus 2. But then as n approaches infinity, 1 over n approaches 0. So you get 1 over 0 minus 2, which is -half. So the sequence converges to -half in this example Bn. All right? Next page. Okay, we have a squeeze theorem for sequences as we did in functions. So everything is similar in Cal 1, okay, except for in this case we're talking about discrete sequences instead of continuous functions. So suppose there are 3 sequences, a_n, b_n, and c_n, and we know a_n, b_n both have the same limit L, and we know the sequence Cn is sandwiched between a_n and b_n. Okay, so Cn is greater than or equal to a_n and less than or equal to b_n. For some after some terms, okay, and greater than capital N. So you can see from the graph what the situation is. The red points represent the sequence A_n. So I just plot the points for A_n by red point, and then the blue points is no. Okay, the red points are B_n. Okay, the big ones, and then the top, the bottom one, the blue points or dots are A_n. Okay, so then the black points are sandwiched between red point and the blue point. These are terms of Cn. Okay, you can see. Now, because both A_n and B_n have the same limit n, they approach the same number on the right. So then they squeeze Cn to approach the same limit. So then the limit of Cn has to be the same to be L, right? If you have 2, curves, one on the top and another one at the bottom, they approach the same number on the right, then any curve in between must have the same limit as them. So this is basically the same as this theorem in the functions. So another version of squeeze theorem. Okay, so we can use this theorem to find the limit of some sequences. Okay, let's try to do some example. One example. Okay, so in this case, we need to find the limit of the sequence Cn equals -1 to the n over times 1 over n factorial. Okay, I don't know if you learned the factorial before or not? The factorial of n is the n factorial defined as n times n minus 1 times n minus 2 times n minus 3 and so on, down to 3 times 2 times 1. Okay, so you just multiply all the integers from 1 up to n. That's called the n factorial. Okay, so and then if you just multiply the n factorial starting from the first 4 terms, 1 times 2 times 3 times 4, you're going to get 2 times 3, 6, 6 times 4, 24. So the next term will be 5. So you can rewrite that as 24 times 5 times 6 and so on to n. So when n is large, okay, like 100. Okay, you can also rewrite 2 to the n as n copies of 2 multiplying each other. Okay, so you got 2 times 2 times 2 times 2 times 2, and so on. So n copies of 2 multiplying to each other. So again, you can multiply the first 4 numbers. So 2 times 2 times 2 times 2. So you're going to get the 10. And then you just multiply 2's, okay, at the end. Now, then you can compare, which one is bigger. You're going to see n factorial is greater than 2 to the n when n is greater than 3, right? Okay, so like n equal to 4, you get the 4 factorial equal to 1 times 2 times 3 times 4, which is 24. 2 to the 4th will be 16. So 24 is greater than 16, as we already know. But then when n equals 5, then you get another 5 in factorial, but you get another factor 2 in the 2 to the n. Now, obviously, n factorial is greater than 2 to the n. And if you increase more, then every time you multiply a number to n factorial, it becomes larger. But then in the case of 2 to the n, you just multiply 2 itself. So obviously, n factorial is greater than 2 to the n, right? So n factorial is greater than 2 to the n. If you flip this inequality, it becomes the less. You have to reverse the inequality. So that means 1 over n factorial is less than 1 over 2 to the n. Okay. You can, in other words, you can rewrite it as 1 over 2 to the n is greater than 1 over n factorial. Okay. So now, if you multiply -1 on both sides, you're going to get the -1 over 2 to the n less than -1 over n factorial. Remember, when you multiply a negative number in the inequality, then you have to reverse the inequality. Okay. And this -1 over n factorial will be less than or equal to -1 to the n times 1 over n factorial, because -1 to the n, it just gives you the sign. It's either positive or negative. Okay. But in any case, it will be greater than, in the case -1 to the n is positive, obviously it will be greater than -1 over n factorial, right? When -1 to the n is negative, then you get equal sign. -1 over n factorial will be equal to -1 to the n 1 over n factorial. Okay, so that's why we got this inequality in here. Similarly, -1 to the n times 1 over n factorial will be less than or equal to 1 over n factorial, because again, when n is even, -1 to the n is positive, so you get the -1 to the n times 1 over n factorial to be the same as 1 over n factorial. But when n is odd, then you get -1 to the n to be negative. So that gives you a -1 over n factorial, and that's less than 1 over n factorial. So you get another inequality like this. And as we already got, 1 over n factorial is less than 1 over 2 to the n. Okay, if you look at the same line, in the first or second inequality. Okay, when n equal greater than 3, okay? And we want that because we are trying to find the limit. So why don't we just let the an to be -1 over 2 to the n, and that's the sequence an, and another sequence bn to be 1 over 2 to the n. So one is positive, one is negative, and they got the same magnitude for each term. Then we have, if you rewrite, the last inequality on the previous line. So on the very first, we got -1 over 2 to the n. That'll be an we defined, and -1 to the n times 1 over n factorial in the right middle. That's just seen in the problem. And on the right, we got 1 over 2 to the n. So that's just bn we defined. So we got an less than cn less than bn. Okay. We just rewrite this in different symbols from the previous line. And that's true for n greater than 3. And we already know the limit of 1 over 2 to the n is equal to 0, as we did in previous examples, if you remember. Okay. This example, we got the limit of 1 over 2 to the n is 0, right? So we can use that term in this problem. So the limit of an equal to 0 and the limit of bn equal to 0 because they are either -1 over 2 to the n or 1 over 2 to the n. So they have the same limit. But as squeeze theorem, Cn is sandwiched between an and bn, so Cn has to have the same limit. So the limit of Cn is equal to 0 also. Okay, so let's use using the squeeze theorem to find limit. Sometimes you have to use this kind of technique. Okay. All right. The next thing is called pattern recognition for sequence. Sometimes you get a sequence reading in numbers listed, and you try to find the limit of the sequence. You need to write the general term, the formula for the sequence from the list. So in this sequence, we got 201, 403, 805, 1607, 3209, okay, and so on. So you can see the top, the numerator in this sequence, in each term is just 2 to the nth power. So you start from 2 when n equal to 1, and the 4 is just 2 squared, so that's second term, and third term is 8, so that's 2 cubed. 16 is 2 to the fourth, and 32 is 2 to the fifth, so that's the top. And the bottom will be 1, 3, 5, 7, 9. If you know a little bit about the odd numbers, those are the basic all the odd numbers, which can be written as 2 and -1. Okay, so for example, 1 is equal to 2 times 1 minus 1, right? And 3 is equal to 2 times 2 minus 1. 5 is equal to 2 times 3 minus 1. 7 equals 2 times 4 minus 1, and 9 equals 2 times 5 minus 1, and so on. So then the general formula for this sequence will be 2 to the n over 2 and minus 1. And then we want to find the limit of the sequence. So in order to find the limit of the sequence, we can define a function based on the sequence. So let's just let f equal to 2 to the x over 2x minus 1. Okay, just change n to x. And then obviously f of n equal to an, right? So this is one thing we just talked. Yeah. So you just replace m by x. So you got the continuous curve, and all the points of the sequence lie on the curve. Okay. So define a function based on the sequence. We use the same technique here. Okay, so fx equals 2 to the x over 2x minus 1 if you change n to x in n. And then we can use the technique to find the limit of a function. So the limit of the function f as x approaches infinity is 2 to the x over x minus 1. We can use L'Hopital's rule. If you remember that, when both the top and the bottom get large. So when x approaches infinity, 2 to the x approaches infinity, and 2x minus 1 also approaches infinity. So then you can use L'Hopital's rule to take the derivative of the top and the bottom. So you got 2 to the x times ln 2 on the top when you take a derivative of 2 to the x, and the derivative of 2x minus 1 is just 2. So then you see you got 2 to the x on the top, and then you get the whole thing multiplied ln 2 times 2 over 2. That's just constant. So but the 2 to the x just gets large, approaches infinity as x approaches infinity. So the limit of the function as x approaches infinity is just infinity. So an, the sequence, has to be the same limit. So the limit of an is also infinity. All right.